All right. Hello, everyone. Thanks for joining us for the Off by One stream, our first one in May. RSA conference just ended in San Francisco. If anyone happened to attend that, I only was able to go for like a day. I wasn't speaking this year, so I was more worried about getting my DEF CON CFP proposals put in. But cool. Welcome, everyone. I'm going to give it a couple seconds here. As usual, it takes some time to connect to LinkedIn and YouTube and X and wherever else it's happened to be streaming. But appreciate everyone. Thanks, Green, for joining as a new member. Really appreciate that. A Neuralink. Yeah, I'll work on that one. Cool. So this week we've got Nathan here joining us. And I first came across Nathan's work somewhere. I think I saw a retweet by someone on X. And the title of the paper, the blog, caught my attention, of course, because obviously, as most of you are well aware, the number of exploit mitigations on the Windows userland and also in the kernel has grown exponentially since older operating systems like XP and Windows 7. It used to be the case, I think, a long time ago that a lot of the mitigations were focused on userland because that's where most people were targeting, because the kernel is like this scary place. A lot of people avoided it. But then there ended up being so many mitigations put into userland that the kernel didn't seem so scary. And I remember early on, like with the kernel on Windows 7 and Windows 8, especially 32-bit, the amount of entropy with ASLR for randomization was way, way lower in the kernel than it was in userland. Like drivers, for example, the first attempt at randomizing driver load addresses was only 5 bits of entropy. So 2 to the 5th power. Obviously, that's pretty weak. And I think some of the reasons as to why the mitigations weren't enforced so strictly in the kernel could have been it was less targeted at first. Also, if a mitigation breaks an application or a process in userland, like a Chrome browser, it just crashes that process. It doesn't crash the whole operating system, as where obviously if a mitigation has some kind of issue in the kernel, you're going to blue screen your box. There's also performance considerations. A lot of these mitigations, there's obviously code involved that has to execute, and some of the mitigations have pretty high overhead. So if it's something in the kernel versus per process level, then it slows down the whole system. But as you can imagine, the more people start attacking the kernel, the more our processors get faster, the more resources we have with RAM and everything else, all this stuff becomes more doable. We still see the mitigation like shadow stacks and control flow enforcement technology, kCET, rolling out more and more as processors start catching up, where I think it was an Intel Tiger Lake CPU was the first one on that side that supported things like shadow stacks. So all good stuff. We've definitely had some streams recently talking about a lot of this. Cool. So Nathan, if you want to go ahead and give a quick introduction to yourself, a little background, that'd be awesome. And thanks for joining us all the way from Paris, France.
Hi, Steve. Well, I'm Nathan, Nathan in English. I work as a pen tester in my day-to-day life, but I am also very interested in low-level security, operating systems, kernels, and exploit development, and in particular Windows. So yeah, I've been interested in Windows for a while. I've published a few blog posts, and this one focuses in particular on shadow stacks and how you can kind of get around them on Windows.
Yeah, awesome. Yeah, and I think we just had a couple presentations recently talking about things like kernel shadow stacks and that mitigation and kind of what it means for us. And we've also had Connor McGar on talking about HVCI and getting around that, and just the overall virtualization-based security initiative that Microsoft has done. And Nathan and I were talking just before the stream. It's interesting that the last conversation I had with some folks at Microsoft, if you know who I'm talking about, you know who I'm talking about, some higher up people were saying that they're going to start slowing down, I guess, on focusing so much on mitigating different bug classes or techniques that we use, and more so on secure code initiatives, migrating over to Rust and other things that should solve that problem and not have to worry about those types of techniques and such as we get away from memory's unsafe languages. But obviously that's going to be a slow process. A lot of the research I've been doing personally and talking with other folks is around utilizing all this machine learning and AI technology to do a much better job at code scanning and stopping bugs from obviously getting released in the first place. So hopefully, I guess I'll say from the attacker perspective, if as new techniques are discovered, the kind of value of trying to mitigate it versus just moving away from it will not impact newer techniques. In other words, hopefully we'll still be able to use techniques like the one that Nathan's going to present for us today. We'll put the blog post up if you hadn't had a chance to read that. I did tweet it. I put it up on Discord if you want to check it out in more detail. But thankfully, he's going to walk through a lot of that today. And as I was saying, Nathan, before we started here, and also anyone who has questions, please do post them. If they're related to what is being talked about or demonstrated at that time, I'll certainly interject and ask the question. If it's something more general or not related to what we're doing right at that moment, we'll hold off on those to the end, but definitely ask questions. I did say on Discord, I don't know if people on X saw it or not, because I don't think I tweeted it, but I'm going to be giving away $100 US Amazon gift card during or as part of this stream. I get a lot of people DMing asking for help. I live in this place and I don't make much money and I need to get some resources so I can do research. Of course, we'd love to help all the people. And as you know, all the proceeds of this channel goes back to the community. I don't keep anything. 100% goes back. Hopefully, if I get accepted to DEF CON this year, I'll be able to give away my extra passes again like I did last year. But the winner of the $100 gift card on Amazon will be based on whoever asks the most creative question or interesting question related to this topic we're going to be discussing today, and post that on YouTube. So not on here, post it on a YouTube comment, and afterwards we'll take a look at it, and then I will respond back to the winner, and then you can DM me on Discord and we'll get that taken care of. But just to encourage people kind of to think and really digest the material, because I know a lot of times we have more advanced content on here, and I'm expecting this one to be something in the more advanced space, because obviously we're talking about the Windows kernel on Windows 10 and 11 and getting around these mitigations and these techniques. So one question I did have on Discord in advance, and I know, Nathan, you used a bit of symbolic execution, but that wasn't really the main focus. But I think I'm going to have a stream coming up pretty soon, either myself or with someone else, talking about and demonstrating symbolic execution fuzzing. Maybe we'll use something simple like anger or driller with anger or AFL with the fuzzer. But a lot of questions do come in around a lack of kind of understanding how symbolic execution, not just with fuzzing, but just in general, and how things like constraint solvers and all that actually work. Do you want to give a quick kind of explanation on that from your perspective?
Sure. So I use symbolic execution a little bit. It was my first time using it. But the main idea is instead of actually running code on your actual CPU, you don't really run the instruction. But what you can do is you use symbolic execution, which what it does is it emulates in some form the instruction, and you don't have the actual results. Let's say you have an add instruction. You don't actually have the results of the instruction, but you have a variable that says it is the addition of this register and this register. And with this, you do it multiple times, and you get constraints on the results of certain registers. So if you are focused on control flow, you can say, hey, the instruction pointer is dependent on this register and the addition of this register. But you don't actually run the instruction themselves. And where solver come into place is, well, you have mathematical solvers, which can be useful to simplify the expression that you have. And so you can get an easier expression that's something that can be very complicated.
That's really cool that you did it that way, because I'm curious to see kind of what types of targets you end up getting to and the control you have over those targets through kind of jumping through. It's pretty cool. I think like in its very basic form, obviously, if you have a variable saying x equals 10, and then there's some kind of condition that says if whatever is greater than x, something like that, it's going to go that path versus this path. It doesn't really care about x. It replaces that with a symbol, and then it's able to, like where a fuzzer like AFL might just do things like bit flips and byte flips and test for mathematical issues and adding random data and splicing, and might just try all these kind of things and then see what happens when that data goes in and it causes a crash, but it doesn't know why it caused a crash. So when using symbolic execution, it can kind of go through and read the instructions and kind of solve and determine, well, oh, it's crashing, but this is the value it needs to be in order to go that way. This is the value it needs to be if it go that way. It's like kind of simplifying an explanation there, but I think it'll be a cool stream idea for us for sure. So cool. I guess if you want to give us kind of a high-level overview of what you solved, the problem you solved, and what you accomplished with your blog, and then we'll just move into demonstration pretty quickly here.
Yeah. So as you said, Windows, especially Windows 11, you have a lot of mitigations, right? Microsoft has been trying to kill arbitrary kernel code execution in multiple ways, and you have two main ways to do it, right? You can either map new code. Let's say you have a vulnerability and you can manipulate memory. And well, you could, for instance, create a new mapping, a new page, then you say this page is executable. This is the first way, by manipulating page table. And the second way is by loading a driver, right? So for both of them, what they did is they used VBS, which has a lot of features, but two of the most important part of these features is code signing. You have a hypervisor code integrity. So with this, you can't really have a driver loaded if it's unsigned. And to get a driver signed, you have to ask Microsoft, right? And for the mapping of a new page as executable, they have secondary level address translation, which says, well, you have actually an extra mapping that's not in the control of the kernel, but a mapping that says this page is not executable. It's controlled by the hypervisor, so Hyper-V, and Hyper-V say it's not executable. So if you try to execute your newly created page, well, you're just going to get fault, and you will not be able to execute the code that you want. So if you're trying to build a payload, well, you don't really have the option of creating new code. So you have to reuse existing code. So code that's present in drivers that are signed and already loaded on the machine, right? So to do that, well, you have to find a way to reuse code, because the code that you will find is not doing exactly what you want, right? It's meant to do some function, and you want to do something else, but you still want to use the instruction. So that's the basic of code reuse. And the most common way code reuse was done in the past is through RUP. So you would use gadgets ending in a return instruction, and you would build a RUP chain and reuse bits of code so that you could execute functions that you're interested in. And this is a topic that has been covered extensively. And so you know that if you can create a rope chain and you are in a situation where you can start a rope payload, well, you will be able to get code execution. You will be able to execute any function that you'd like with any argument, and you will be able to execute code that's not your own, but still do what you want on the target. But recently, there has been a new feature on Intel CPUs, which is the shadow stack. The shadow stack is meant to prevent this kind of code reuse. When a return instruction is executed, you have a comparison that is done between the value that was pushed to the stack during the call instruction and the value that was pushed by the same call instruction but on the shadow stack. So if you have a vulnerability that lets you edit the stack, you can tamper with the return address on the stack, but not on the shadow stack. The shadow stack itself is protected by a specific CPU feature. So you can't really craft a rope chain, because if you put an invalid address that was not previously pushed by a call instruction, well, the CPU will generate a fault, right? So we have to find other ways. And that was the whole idea of the technique, was to try to find a way to reuse existing code and not using this technique. So RUP was used in the kernel I think a good example, there was a library called Kernel Forge, I think, which does something which is pretty simple. It creates a new thread, and it suspends the thread gets suspended in the kernel, and the library edits the stack frame of the target thread, and it creates a rob chain on it and resumes the thread. And so that worked great, but if you have CET enabled, well, it doesn't work anymore. And Windows added support for usernode, but also kernel CET. So on the most recent Windows version, if you have a CPU that is compatible, you can have Intel CET enabled, and you can prevent ROP on the kernel. So ROP is only part of is one of two elements of Intel branch tracking. You have the backward edges and the forward edges. So CET is meant to protect the backward edges when a function returns. But you have forward edges when you either call a function or jump to a function or a branch you're interested in. And you can have indirect jump or indirect calls. And those are not protected by CET, by the shadow stack. So my idea was to say, hey, how can I use these forward edges to get code execution? So there is something that is quite well known, and I had a look about how it's implemented, is jump-oriented programming. So jump-oriented programming is quite different from ROP chains. On ROP chains, you have something which is more powerful, because when you do a return statement, you update the instruction pointer. So this is the same for a jump-oriented programming, right? You're going to jump to a value you control and update the instruction pointer. But if you do a return, there is something which is very interesting, is you update the stack pointer. And this is very powerful, because when you update the stack pointer, you update the state of your payload. So when you build a ROP chain, you don't have to worry about updating the state of your payload. When you execute one gadget, when the gadget is done, you automatically go to the next gadget. And this is not something that is the case with jump-oriented programming, because your gadgets are going to end in a jump, but there is nothing to update the stack pointer or something holding the state of your payload. So this was the first element of, that was important for me to understand and to try to be a technique that would work around this. So I'm going to share my screen now.
Great. Yeah, remember the first time dispatcher was?
Yeah.
All right.
Can you see my screen?
Yep, I'm going to pull it up right now. Cool, there we go.
I have a Windows VM, doesn't really matter, and I have a debugger attached to it. So to do this, you have to look for a jump dispatcher. So this is a gadget, a job gadget that will be used to update the state of your payload. So the idea is you execute one job gadget that does something useful for your payload, and then this gadget jumps. And it jumps back to your dispatcher, which will do two things. It will update the state of your payload, just like the update of your stack pointer when executing a return, and it will jump to the next gadget. And the next gadget will do a bit more, jump back to the dispatcher, and so on. And so, well, to get this working, you have to find a dispatcher. It's really the most important piece of your payload, because you will have constraints on the job dispatcher, and so you have to find it first if you want to design your job chain to work around the constraints of the job dispatcher. So the first one that I found is not the one I ended up using in my blog post, but it works nonetheless. So it's this function. So this function, we can ignore the first instruction. I hope you can see fine. Starting from the second instruction, let's assume we control the RDI register, this snippet of code will update the RCX register and jump to it. So this is great because this is the part that lets us edit the control flow to be whatever we want, and it also updates the RDI register from a value that's pointed by the RDI register. So initially I thought, well, I'm going to use this gadget, and I started building a job chain using this gadget, and it worked quite well. But I found a second gadget that was even more powerful after some time, so I ended up switching to this one. So this one, I will copy the name because it's quite long. There is also something that's great about this stub. It's, in my opinion, this is unwritten assembly. It's not a function. It doesn't use a standard calling convention. Nothing. It looks like unwritten assembly. So this is great because it's unlikely to change in different Windows version because the compiler was changed or something changed, right? So if we want to build a technique that we can reuse, well, this is nice to have a dispatcher that we can reuse. So the second function is this function, which is a bit bigger. It's related to control flow guard, which I will be talking about in a few moments. But if we start from here, this instruction, we can see this function is very powerful, or the snippet is very powerful, because we can control RCX, DX, R8, R9, and jump to a value that we can control, the value that are pointed by the stacks. So this is very similar to a rope chain. We are going to put our arguments to what we are calling with calling the function with on the stack. And this is really great because just before this instruction, we have a call RIX. So if we use this call instruction, we are going to return it here. And this is a fine job dispatcher. So this is great because we can call and have a job dispatcher. And the call is more powerful than jump. I will be talking about that. So the idea is if we can get this payload execute in a loop, so we update the first 4 registers that are used as argument in the fast call convention. Jump, I know it's the same register, but let's pretend we can jump here, call a target function. The function will be called with all arguments control. And at the end of the function, there will be a red because it's a legitimate function. So we will return here. We'll update arguments again, jump back, etc. So the idea is to have some sort of loop. And this dispatcher is more powerful because we have this call instruction here. I hope it's clear. So obviously there are some constraints, right? First, it's the same register that is used in the jump and the call. So we can't jump here, and otherwise the call will loop and execute this instruction, and we will get a stack overflow. But if we can find a gadget that just updates our AX and jumps here, well, it's great for us, right? And so this is the main idea, because if we were to use the previous gadget, so this one, we end in a jump. So we can't directly jump to a function, because if we jump to a function we're interested in, at the end of the function, there is a return statement. And so this return will not be able to return after this function, right? It's not a call, and we lose the execution flow. So we would have to find a call followed by a jump gadget, and we would jump to the call. It would call the target function, return back to the first jump, and this jump would return to the dispatcher. So it's more work, and this is more powerful, so I went with this gadget. Once again, this function is a very specific calling convention. You are supposed to pass in the RAX register the target function you want to call. So this is probably unlikely to change in the future unless they explicitly decide to change the function. So for a technique that can be reused, this is great.
Somebody on Discord was asking how common, how likely is it to find one of these dispatchers like that? Are they all over the place, or is it rare?
I would say it's pretty rare. I only looked at NTOS kernel. I did not look for dispatchers within drivers, but there are, the difficulty with job gadgets is most of them are, if you use a tool to list gadgets, the vast majority of them are useless. And there is a lot of them because there is a lot of code in the kernel. So it took me a while to find this one. And I was so I found it using manual analysis. I just looked at a bunch of job gadgets, and so I would say it's not very easy to find one. But I only looked at NTOS kernel, and I found 2. So I think there are a few, but it's not very common. So now that we have the idea for the main loop that will execute our payload, we have to define a bit more what our payload is going to be, and how do we get to this loop that calls this dispatcher and target function. So what I wanted to do for my payload, I thought I want something that's not easy to do with just an arbitrary write. So I don't want something that you can just, I don't know, replace a token of a process. I didn't want to do that. I wanted something that would be painful to do using only arbitrary writes. So what I chose to do was a keylogger. And the main idea is to find a specific driver and create a new mapping of some memory of this driver and map it to username. And for this, we are going to use Windows APIs, the kernel APIs, and Windows does all the hard work for us, right? We don't have to manually edit page table entry, which would be very painful, and I don't want to do that. So our payload is going to be calling specific Windows kernel API function in a specific order, and we need to be able to capture the return value of these function calls. So for instance, here it's not great because we are going to lose the return value of this instruction. Just here we update RAX, so we lose the return value. The second constraint that we have is how do we get here? There is something I haven't talked about yet, is Windows has some form of forward edge protection. But the difference with CFG, which is Windows implementation of forward edge protection, is it's a software implementation, unlike ShadowStack, which is a hardware implementation. And it's much weaker. It relies on having every single jump and call instrumented. So you add a check to verify that the target function of the jump or the call is valid. And by valid, it means it's within a bitmap that represents all the function in the kernel. But it's weaker than Intel hardware equivalent, because if you can find one spot where, for instance, the jump or the call is not protected, you can jump to this dispatcher, and here we have no instrumentation, right? We can loop around, and we are not constrained by the forward edge protection, which would be the case if they used Intel branch tracking forward edge protection. So how do we get around CFG? I'm going to start with this, and then I will show you the payload and how I built it. So how do we get around CFG? In a previous live stream that you did, Conor McGar said, well, you can, one of the ways to do it is to replace an import address table entry with the function you're interested in, and calling a function that would use this entry and call the function that you're interested in, because these calls are not protected by CFG. I chose a different approach, so this is why I had a look at symbolic execution. My idea was to take all the valid functions within the kernel all the valid targets for call, and use symbolic execution to execute this function and see where the instruction pointer would go and if it could be controlled depending on the something that we could control. So for instance, let's say we have a vulnerability that lets us control a function that will be called and the second argument. Well, we are going to be looking for a function where the instruction pointer will be controlled by the second argument or dependent on the second argument. I did that, and I also had a look at functions that are notoriously hard to track for control flow enforcement. So I had to look at stuff like long jump, which is used in exception handling. And long jump is quite specific. So long jump, you pass in the first argument buffer, which is supposed to be an opaque structure, but it's just a list of registers, and it reads all the register from the structure and jumps to the function. So if we have a look at the function, it's not long jump. We have two functions that are called. We have check stack and target address, and long jump internal. So the check that is performed by this function is twofold. You have the target address. So the only check is actually checking whether it's a kernel address, so whether the topmost bit of the address is 1, but nothing else. It doesn't check that it's a valid function. And it makes sense because you can long jump in the middle of a function, right? And the check stack part of this check is it checks with whether the RSP value that you supply in the buffer is valid within the stack, the bottom and the top of the stack of your current thread. So it's not really a problem for CFG. And then it calls long jump internal, which actually reads the registers and jumps to the target function. So it reads all registers that we could be interested in, and it ends up jumping to this register, which is controlled by the structure that you supply in the first argument. So this is great. There was something I was not aware of with long jump. So long jump is a valid CFG target, but there is a flag that says, hey, this export is suppressed. So actually, these flags means, well, you shouldn't be able to call long jump as a valid CFG target, right? So if you have a CFG check, it should say that long jump is invalid. But this bit is actually ignored by the Windows kernel. It's not the case in user space, but on the kernel, this bit is completely ignored. So we can just call long jump and specify a buffer that will have a valid kernel address, but that's not a valid, for instance, for dispatcher, that's not a valid CFG target. And we just specify a stack address that's within the bound of the kernel stack of the current thread. So that's the main idea about to get around CFG. But there are other ways. With my symbolic execution approach, I found candidates that could be used to get functions that just simply do not implement the CFG check. So I think we could find a lot more techniques to get around CFG. So now I want to show you the actual payload that I built. So I didn't want to use a vulnerability to actually prove this because I don't have a vulnerability at hand. But what I ended up choosing was a technique called kCET, which was previously published. And so this is an admin to kernel vulnerability, but Windows doesn't, Microsoft doesn't not consider this a security boundary, so they choose not to fix it. And we have a bit of setup to be able to reach the target function, but what primitive does this give us? Well, essentially, we are going to be able to be calling this function. Why does it? Is it not the right one? Why? Okay. So this function, we control two values. We control the values that are pointed to by RCX, and well, we control RCX, so we can control the values pointed to by RCX. And so we can see that we are going to be able to control RAX, which is the function that will be called. It has to be a CFG valid function. And we control the first argument. We actually control more, but we are going to ignore this one. So the primitive that we have is we can corrupt a pointer that will be called, and we control the first argument. So if we look at the job chain itself, it's quite long. So what I don't want to go around the code. I don't think it's very interesting. But what we will be doing is actually executing it, and we will go step by step to demo how it works and understand the loop and so on. And why is my VM stuck? Oh, because I obviously. So it's an admin to kernel vulnerability, so I have to run it is in this payload in high integrity context. So I will put a breakpoint here, so we can see the start of the execution of the payload. So we are at the part where we get to start the execution of the call. So the function we are calling is, as I said, long jump. And if we look at the first argument that we are passing, there are only a few values that we are interested in. We are passing a valid stack address. So to do this, I use the fact that on Windows, you can leak a lot of kernel addresses. It's not the case on Windows 24 H2. You can't do it anymore if you're not a local administrator. But we are here, so I just leaked the addresses. If you were to exploit an actual vulnerability, you would have to, on Windows 24 H2, you would have to have a leak to get around CFG here. So we have two things. We are passing this function, which will be the function we are calling. And if we look at what function does this correspond to, it's the first job dispatcher. So if we look at what I did, the idea is to just reuse this dispatcher just once. Afterward, we will be using the second one. The second one requires control of, if you remember, of the stack values. Here we have to control the values on the stack, so we have to control the stack pointer. And to do this, we are going to call, sorry, I'm looking for it. We are going to call long jump internal as a target of the first long jump. So the RIP that we are specifying in the buffer to the call of the first long jump is long jump internal. As you can see here, we will be jumping. So I will be put a breakpoint here. So where are we jumping to?
Good old hardware abstraction layer, yeah.
Yeah. Oh, so I remember this. So we are going to call long jump internal, but we jump using the RCX register, so it doesn't really work. So we have I just use a simple gadget. I just move R13 into RCX and call RAX. So if we look at RAX, it's long jump internal that we will end up calling, and in R13 we have the second context that we are passing to long jump internal. This time we have no constraint on the stack, and we can just pivot the stack anywhere else. So if I put a breakpoint here, so now we have long jump internal that's being called. So this is the target of the second long jump internal that we are going to jump to. And as you can see, this is the second dispatcher that I used. But we are not starting at the call instruction. We have not set up anything. We are starting the execution here. So we can control all the first 4 arguments and the function, the jump, where will we jump. So this one I will be reusing. So if we have a look at where do we jump. So if you remember what I said earlier, I said we can't directly jump back to the call instruction because it uses the exact same register. So this is not perfect. So instead, what I did is, I jumped to a gadget that will update RAX and jump here. So this gadget works well. We can ignore this to the instruction. It just reads RAX from the stack, and with the previous step, we now controls the stack, so we can put whatever we want, and we have to control RSI to be able to jump back to the call instruction to start the loop. To do this, I use the fact that long jump lets us control all the registers, including RSI. So this one is just a way to see if we have a look at what's on the stack. So this is the actual call jump gadget that I also mentioned earlier. So the idea is we want to call function we're interested in, but we also want to capture the return value. And if we do it directly using the call instruction, it doesn't work because it gets overwritten in this instruction here. So how does this work? Well, we are going to call a function. So this function is a Win32k SGD function. So it's the session driver. This is used to retrieve. So inside this driver is where the data we're interested in is located. So the state of your keyboard is represented within, is managed by this driver, and you have a bitmap that represents the state of each key on the keyboard. And so we are going to use this function to locate the address of this bitmap. This function is specific to Windows 11, so this technique is not mine. I used someone else's technique, but this is specific to Windows 11, where they introduced this driver. So we need to call this function, get the return value, add a constant offset, and then create a memory mapping and map it to username. So this is great because I can demonstrate calling arbitrary functions and actually performing arithmetics on the pointer we get from this function. So let's go add a breakpoint here. Okay, so here we are calling the first function we are interested in. And if we look at what's on the stack, obviously I did not, that was not the best idea. So this is not the correct thread. I forgot what my thread was. I should have added. No, not what we're interested in. Okay, so if we look at the stack, so this is the normal stack. And if we look at the shadow stack, we have this address, which is exactly this, the jump that follows the call that we saw previously. So we are returning, at the end of this function, we will be returning to the address that is on the stack. And it's also the same on the shadow stack. So we will not get any problem with Intel CET because we are actually respecting the constraints of CET. We are not returning to an address that was not pushed to the shadow stack. So if we add a breakpoint here, I will this time add check for our process. Here, I will just disable the previous one so we are not bothered with. So if we look at it, we have the value we're interested in is this one. So we want to save this value, and we want to return to the dispatcher because we have to keep the execution of the loop, right? I said that we had to control RSI. We also have to control RSI to jump back to the loop. So we had to control RSI previously. It was here to be able to call the function we're interested in, and we also have to control this one. But since we control it once, it's not a different constraint, right? So it's not an issue. So let's see, where do we end up? So here we have to save RAX to be able to reuse it later on the stack, to reuse it for other function calls, sorry. So this one is interesting because we have to find a way to save RAX, and actually finding it's not so easy to find a gadget to do this. So I use this one, which saves it to the value pointed by RSI, so which we already control, so it's not a problem. And so if we look, we will return a second time this time. So I will add a breakpoint here.
How much of this work around finding the gadgets and such was manual versus something you were able to automate in some way?
Almost all of them were manual.
I was thinking.
Yeah, almost all of them were manual, but my thinking was I want something that can be reused, and I don't think, I think finding dispatcher is not easy, but finding gadgets to, for instance, control RSI or save RAX and so on, it's not that hard, right?
Right.
It's not the most difficult. I'm pretty sure that even if they remove this function, it's finding a way to save RAX is doable. Same for a call followed by a jump, it's still doable. So yeah, I think the dispatcher is much more difficult to find than all the other gadgets. So these gadgets, I did not check whether they were present on other Windows version. I only checked on this version, but I'm confident that we can find them on other Windows versions.
Are you using a tool to help you find the gadgets, or are you just manually searching?
Yes, I'm using RP++ by Axel Souchet, which is great. I would recommend using it. I don't have the link right now, but I can add it at the end. I think it's it's great because it lets you search job gadget as well as rope gadget. Most tools let you only search for rope gadget, but this one lets you search for jumps. So that's great. And this time we are going to return. And if we look at where we are returning, we are returning back to the loop. So we had two calls. The first call was from the dispatcher. The second one from the call used to save, well, to not overwrite immediately after the return value. And now we jump back to this function. We are back again for another round of the loop. There is something very cool about this. So here we end up going back here and here. So once again, I will use the same gadget to update RAX. So we have to clean up the stack. Doesn't really matter, and update RBP. I will skip this step, which is not the most interesting. And here we are back calling another function. There is something great about this, is because we are using a call and not a jump, we can actually call wrap gadgets. We don't have to call the start of a function. There is no CFG check, so we can call wrap gadgets. So this expands the pool of available gadgets, right? Which is great because job gadgets can be complicated, right? this gadget, I have to ignore 2 instructions which are not very relevant, but I have to ensure that they do not crash, they don't do anything that would corrupt the state of the machine. And rob gadgets are usually a lot simpler, and so using rob gadgets is great. So now we have updated RBP to call a second function using the call jump function. So if we have a look, this one is a rob gadget, as I mentioned. It's simple, simply xadd. We can ignore the log prefix. We don't really care about it, and we don't really care about the exchange part of it. So we can consider it just a simple add gadget, and it's going to perform an addition to add a constant value to memory control. So we are going to add a constant offset to the value that was returned previously by the win32ka sgd function, this function. Because this is a structure, the function returns a structure which contains the bit field containing the state of the keyboard. So we have to locate it. And so if you look here, where, oh yeah, did I miss it? I think, what happened? Oh, I think, oh, I know. So it's disassembler that I don't, where did I place my breakpoint? Yeah, I should hit it. So I'm not sure what I did. Let me have a look. Oh, so okay, I was just ahead of myself. Why did it not get called, or why did not my breakpoint not hit? If I go, oh, I think, okay, I definitely should have. Let me restart from scratch. This time I will add a check for the process, so it's easier to see for me. Let me restart.
Someone on Discord's asking, how many hours do you think you put into getting through this whole technique? Like,
I think having the main idea of, once I had the dispatcher and the main idea to make it loop and use the call instruction, I would say maybe 10 hours, something like that. But finding the idea and the dispatcher, it was something that I did over a long period of time. So I can't say the definitive amount of hours, but it took a while. I had been thinking about this for a while. Last year there was a FRAC paper which was kind of similar. It was on Linux username, a way to get around shadow stacks, but also internet branch tracking. And I was thinking, how can I adapt this to Windows? So I don't have a definitive answer, but it took me a while. But once I had the technique, yeah, maybe 10 hours, because I had to debug it, I changed the dispatcher, but I don't think it was that difficult. It was just debugging a job chain, which is tedious but doable. So apparently I crashed the machine. Let me restart from my checkpoint. I didn't have many, I think it should be fine.
have you played much with counterfeit object-oriented programming?
Sorry, I couldn't hear what you said.
I was saying, have you played much with counterfeit object-oriented programming?
So I read about it. I didn't get to play around with it. I would say it's not very applicable, because here all the gadgets were taken from the Windows kernel, and most of it is not C++, where you could find counterfeit object-oriented programming gadgets. So you have to have C++ applications, but the ideas are kind of similar, right? The idea is to corrupt virtual table function pointers and get this kind of same mechanism. So I think some of the ideas are similar, but not applicable directly. So this time, let me add checks. For the process, and here we go. So we're going to be calling. I'll go back to where we were. So I will add breakpoints to the call instruction and the jump instruction at the end. So we can see the loop. So first we get to the jump, just like before. We go to the call. So this time we are going to call again the function to get the return value from the Win32k driver. This time we are going to go back to the call instruction, and we are going to change RBP to be the next gadget, because we are going to call RBP. So we get to the jump, and again to the call. This time we're going to get to the call RBP, and this time RBP holds the XAD gadget. So okay, this time we hit the breakpoint. If we have a look at the data here, it's the bitmap that is it's the bitmap that contains the structure that contains the bitmap that contains the state of the keyboard, and we have the offset that is a fixed value. So we can actually reuse a rob gadget to edit these values. So that's great. This time the gadgets end. We go back to the jump. We go back to the call. If we look at what we're doing, we are once again updating RBP, which will be our call target. We go back to the jump. We go back to the call instruction. This time we are going to once again call RBP. If we look at what's inside call RBP, we have memcopy. So why memcopy? Well, we want to be able to reuse the value that was returned with the addition, right? And so to do this, we have to we want to reuse as an argument of a function call. So what I did is I built the payload in 3 parts, and at the end of each part there is a stack pivot from one stack to another part, from one part to another part, and we have to write the value that was previously calculated here, so the addition, to the second part of the payload, so we can use it as an argument to the second part of the payload and to a Windows API call. So we are going to do this, and we go here. So if we have a look at what we're doing here, once again, we're controlling RBP. Yeah, sorry, this is what I wanted. And so this time, this is a bit specific. We are not calling an actual function, we are calling this function, so the following instruction. Why is that? Well, you will see. The idea is we do this to push this value to the shadow stack so we can return to this address. So if we look at the stack now, we have this address here on the shadow stack and on the stack as well. But why did it write this? And we are going to pivot the stack. Oh, this is okay. I know why we are pivoting the stack, and there is a red gadget, so we have 2 values, so it's offset by 1. So if we look here, here we are updating the stack pointer. And then we are going to return, and this is the value that was previously pushed. But this is, I think, interesting. So this is one of the limitations of the shadow stack. We are returning to an address that was pushed to the shadow stack, so there is no violation. But if we had a look at where it was pushed, this is not the same value. It was not pushed here on the stack. It was pushed somewhere else and overwritten. But as long as it's the same value, you can return to it, right? And you can't do it even though it's the same value, but it was not pushed here. So this is one of the limitations, I think, of shadow stacks. If you can call function and push valid return addresses you're interested in on the stack, well, you can return to them. And so now we have updated the stack, and we have pivoted to the second stack. And so we can do the loop once again. We are calling RPP. So we are allocating a memory descriptor list. This will be used to create a new mapping for the kernel memory so that it's mapped in userland as well. Update it. I think I removed. Did I remove my breakpoint? No. So we are doing the same. We are the allocated MDL. We need to reuse it to actually. The memory descriptor list is just a descriptor. So it describes the memory that was written by the Win32k driver and the addition. And we copy it to the third part of the payload. So domain copy. Once again, where is it stuck? What have I done? We are still in this process. It's a bit difficult to debug, so this is why it takes a while. I think reading the... I don't know why this breakpoint...
No, you're doing an amazing job keeping track of everything, so I'm impressed. So.
I'm trying. So I will disable it for now. Okay, so this is the... I don't know why this breakpoint was getting called over and over. So at the end of the second part of the payload, we are pivoting to the third part, so I can show you each part. We have... so this is the structure that I used. So for the main loop, we can call and jump back a number of times, and at the end we use a way to update the stack pointer to the next part. This part we do the same. We call IO allocate MDL. I don't think it's very important to show the other steps, but the idea is to call all of the steps. So we are calling IO allocate MDL to create a new MDL. We are probing and locking using probe and lock pages. So we can actually lock the pages so the physical pages don't move around. and we are using a function which has a name. This is very long. Can't remember the name of the top of my head. map locked page specify cache. And once this is done, it creates a new mapping in New Zealand. This time, we have this new mapping in New Zealand, which is the same physical page than the one in kernel for the Win32K driver, and it contains the state of the keyboard. So now if I go to, let's say, Notepad, as you can see, it's starting to work here. So you can type and it gets updated. Right. And it works. So I did not handle every single key properly. So you can see some of them are not properly handled. But you can build a better keylogger if you really want to. It's not very relevant, right? I think. So that's the main idea. Of course, the payload is quite large, I would say, just to call 3 functions. This is, and obviously it doesn't even take into account, setting up the state to be able to use this admin to kernel vulnerability, etc. So it's definitely a lot of work, especially compared to rob chains. So once I had done all of this, I think something interesting to think about was, when is this useful? I said I wanted to do something that was not easily doable using an arbitrary write. This would be difficult using an arbitrary write, but technically you can still do it. I think the most value you get from this is if you want to execute a privilege instruction. So if you want to edit debug register, control register, or performing some specific operation that requires you to be in a privileged context of the CPU, well, this is one of the ways to do it, but it's most of the time it's not going to be useful if you have a vulnerability that lets you get an arbitrary write. What you can do is edit your token, get to local admin, and then use admin to kernel vulnerability to use this kind of technique to execute privileged instruction if you really want to. But I think the use cases are limited to either privileged instruction or complicated kernel APIs. If I had to do this using an arbitrary write, this is a lot of steps, but if I had to do everything using an arbitrary write, it would also be a lot of work, I think, especially if you want to keep it consistent across Windows versions. So I would say it's a trade-off, but it's clear that kCET and ShadowStack make it a lot more difficult for someone who wants to exploit the kernel and reuse existing code. It's doable because the forward edge protection is not great, but it's a lot more work, and it's quite, the use of actually getting arbitrary code, kernel code execution are limited compared to arbitrary write, right? I hope that makes sense.
Absolutely. Do you think you could probably use this with kernel mode, implants, right, to get around the EDR that's in there, and with Cobalt Strike or something?
Yeah, totally. But this is also something you can do using arbitrary write. And I would say it's even easier to do just using an arbitrary write, because you only have, most of the time, all what you have to do is only overwrite a pointer and clear it to use a dummy function that does nothing. So I would say even an arbitrary write in this case is sufficient. So yeah, the use cases are limited, but I think it was very interesting personally because I had to learn a lot about ShadowStack and control flow enforcement in general. It made me think about all these things to realize that, yeah, actually the use cases are limited. And if you're an attacker, most of the things you will be interested in are available only using an arbitrary write.
Right. How much the shadow stack constraint that you had to deal with, like making sure that you're returning to something that's you pushed on, that exists on the shadow stack that you're putting back on the active stack. How much of a constraint was that with regard to maintaining control? Was that did that take a while to figure that out, or is that pretty easy part?
I would say not so much work because there is only one step where I actually do something that's kind of unexpected, where I actually write the value myself to the stack. And it's not a call that just writes it to both the normal stack and the shadow stack. So for most of the execution of the main loop, it's only when I want to transfer between one part of the payload to the second one, I have to do this. But other than that, I don't really need to do this. So most of the time, I don't even have to think about it because I'm only executing code that are returning where they're supposed to return.
Cool. That's super cool, man. I'm impressed. Good job.
Thank you.
Did you happen to submit to DEF CON or any other conferences?
No, I did not.
Yeah, you should absolutely do it. I think it would be loved. So we're wrapping up here. For all of those attending, any questions for Nathan? Ask them now because I'm sure it's getting late where he is right now. It's about 9 p.m. there.
Yes.
Yep.
I see someone asking, was it RP++? Yes, it was.
Right. Yeah, I think mostly just compliments, people saying wow, and that's cool. So we're not too many questions. Let me just double check here. Yeah. Cool. So what I'm going to do, though, like I said at the beginning of the stream, if you didn't hear it, I'm going to be doing a $100 Amazon gift card giveaway to the best question posted on the YouTube video. Once this goes, right when we get done here, it'll get posted on YouTube. A comment left there, that's a question. That's just a really good one. I'll select it, or I'll ask Nathan to select it, and then I will get that over to you. But yeah. Nati's saying, did you use drivers?
So I did not use any gadget inside driver. They were all inside NTOS kernel. But I had to use a Win32k driver because it's the driver that contains the state of the keyboard. So I did not use any driver, whether a vulnerable driver to get the actual primitive. It's built into Windows. Or actually the gadgets, they're all within NTOS kernel. So even if those two, for instance, dispatcher are removed, you can still have a look at drivers, especially built-in Windows drivers, and you could search for dispatcher there.
There's a question from Marie.
So I don't have a strong opinion. I think symbolic execution is definitely useful looking for functions that can break CFG. I think it has a lot of potential because my approach was very limited. My friend that worked for the tool I used said, well, you can do a lot. There is a lot of improvement, a room for improvement. So I think it's very useful for this kind of things. But for reverse engineering in general, I'm not sure, and especially understanding Windows and OS programming in general, I think it's very important anyway.
Yeah, and I want to reiterate something Nathan said, which was, he learned a ton about internals on Windows, like shadow stacks and other things. Like that's a lot of what researching and coming up with these techniques is how much you learn. Even if you're not successful at the end, you learn so much about the internals, and it's really difficult to mimic or replace that without actually going through and doing it. So I see a bunch of people saying, I'm going to have to watch this video a bunch of times to understand it. You're also going to have to get a debugger out and get in there. But cool. Is Microsoft going to patch or prevent this? I was mentioning this earlier. I was mentioning David Weston and some other folks, Matt Miller and all. They've stated, not that that's necessarily going to be true, but they've stated, them being Microsoft, that they're going to be focusing less on patching mitigations. I'm sorry, putting new mitigations in to patch against techniques or vulnerabilities and focus more on secure coding, using AI to do code inspection and prevent bugs to get released, and get moving over to Rust and other things, as opposed to, and I think Connor McGard did a presentation a couple of years ago. He called it nickel and dime mitigations. And the idea was having an operating system vendor focus on obscure techniques may not be the best use of their time. And so I'd be surprised. And Nathan, you said earlier before we got started that you doubt that they'll be putting indirect branch tracking into the Windows kernel. And I agree with you there.
Yeah, I think something that they could patch is the admin to kernel vulnerability that they don't really consider a vulnerability. But this one, I did not discover this one. It was discovered, I think, maybe 1 or 2 years ago. Sometimes they do fix them, sometimes they do not. And I think on this part, they're not very consistent. Yes, some of them were service to kernel, which is quite slightly different than admin to kernel. But I think, they could patch the initial vulnerability, but the technique in itself, I would say it would require a lot more changes.
Yeah, like when you're an interpreter and you type git system, it's using these techniques because Microsoft doesn't see it as a trust boundary. So
yeah, that's the term we use.
All right, I won't keep you anymore. Thank you so much again. Your company that you work for is lucky to have you, for sure.
Thanks for having me.
I will let you know if some interesting questions pop up on YouTube that you might want to take a look at. But otherwise, have a great weekend. Merci beaucoup all that. And see you next time. Thanks, everyone.
Thanks.
Bye.
Bye.